In lecture 9, I will discuss the following points. It's very important lecture related to logic circuit design, and this is one of the main theorem that we discussed and used in most of the problem. It's known as the DeMorgan's theorem, and actually we'll discuss two DeMorgan's theorem, and some part of this DeMorgan's theorem we already discussed in previous lectures when we discussed the NAND and NOR. Okay, there's a relationship between NAND and negative NOR and negative AND. Okay, uh, again we will repeat that, and how we can apply De Morgan's theorem to simplification of Boolean expression, mainly when you uh, calculate the complement of a function. Okay, we can use this De Morgan's theorem, and this is the first theorem. Uh, De Morgan's theorem says that the complement of a product of variables. Okay, uh, please read. A complement of a product of a variable is equal to the sum of complements of the variable. Okay, I'll explain this sentence by using a simple expression that will be very easy to remember. Actually, there is a complement of product of variable. So this is a first sentence, that x into y, and an AND operation between x and y, and we are taking the complement of that. Okay, the entire thing will take the complement. X y will consider as a single time and will take a complement, or simply you can say it's a NAND gate. Okay, x y input and the NAND gate output, x y the whole complement. Okay, and which is equal to uh, x bar plus y bar. Okay, x bar plus y bar, and that is the second sentence, sum of complement of the variables. Okay, this is sum of, actually this is an or operation. Okay, or we can say here you can see the negative or bubbled or. Actually we'll take x here, and if you take not here means it becomes x bar, and y here it becomes y bar, and then we'll perform the or operation, x bar plus y bar. So this is De Morgan's theorem for a two variable. Okay, similarly we can extend this theorem for a three variable or n number of variable. For example, if you are writing x y z the whole bar, okay, which is equal to x bar plus y bar plus z bar. So this is De Morgan's theorem, and in order to prove the De Morgan's theorem we can use the truth table. Okay, this is the truth table. Here you can write x and y combination 0 0 0 1 1 0 1 1, and we need x bar and y bar, so you can write x bar y bar. uh, 0 becomes 1, here the 0 becomes 1, and if you write like this, all zeros becomes 1 and all 1 becomes 0. Okay, you will get x bar y bar, and now we can find x into y the whole bar. So x into y means 0 0, so 0 and 0, and take the complement. Okay, if you perform 0 and 0, it's 0. Okay, then take complements 1. So simply the NAND gate. Okay, here you can see the NAND gate operation, and here you can evaluate x bar plus y bar. So here you can see that x bar and y bar, and if you perform the OR operation between these two values, so 1 plus 1, okay, equal to 1. 1 plus 0, that is the OR operation. Okay, we are performing the OR operation. 0 plus 1 equal to 1, 1 plus, sorry, 0 plus 0, 0. So if you compare these two columns, you can see these two columns are equal. So we can prove De Morgan's theorem, and in two way you can think a bubbled OR is equivalent to NAND. Okay, it's very important. It's very useful theorem. Or whenever there is a term like this, x into y the whole bar, you can split it into x bar plus y bar. So here this AND operation becomes OR operation. Okay, and you need to take individual times. So and now we'll and this theorem is very useful to finding the complement of a function. Okay, we'll see later how we can use this Boolean, sorry, De Morgan's theorem to simplify the Boolean functions. And now we'll discuss the second theorem. It's almost similar to the previous one. Previously we discussed AND operation. Now we'll discuss sum of variables. Okay, and complement of sum of variable. So that is written by x plus y the whole bar. That is a OR operation. Okay, here you can see this is equivalent to a NOR. Okay, x y, and we are taking the NOR. The entire thing will take. Okay, x y will consider as a single term, and we will take NOT for the entire operation, x plus y the whole bar, and which is equal to x bar into y bar, or the AND operation, the product of the complement of the variable. Okay, so here take individual complements x bar and y bar, then we will perform AND operation. So this OR operation becomes AND operation. So this entire term becomes split into two. Okay, that's a second theorem. Or we can think in another way, which is equal to negative AND operation, or we can say bubbled AND is equivalent to NOR. Here you can see x, and when you take NOR, NOT operation, it becomes x bar. Here it becomes y bar, and the AND operation, x bar and y bar. Okay, just like product term. So here you can say this is bubbled AND. So bubbled AND is equivalent to NOR. Okay, so two theorems. One is bubbled OR is equal to NAND, and another one bubbled AND is equal to NOR. Okay, and now we can prove this. First write x and y, then x bar, y bar. Then first we can calculate x plus y the whole bar. Okay, at that time we'll take this x plus y. If you perform here, 0 plus 0, 0, and you need to take the complement, so it is 1. And here 0 plus 1, 1, and you take complement, it becomes 0. Similarly, you will get this particular column. This is equivalent to NOR. And now we need to calculate x bar dot y bar. So these are x bar, y bar. So you need to perform AND operation. So 1 and 1 becomes 1. 1 and 0, 0. 0 and 1, 0. 0 and 0, 0. So we can see that these two columns are same. So from this, we can conclude that this is a valid equation, okay, in Boolean expression. It's a very important theorem, Boolean concept, DeMorgan's theorem. Now we'll perform some simplification based on this. So here you can see that apply DeMorgan's theorem to the expression x y z bar. Okay, we can extend. We already explained two Boolean's DeMorgan's theorem for a 2 variable. Now we need to apply for a 3 variable. So here you can see that x bar, y bar, z bar. When you apply DeMorgan's theorem, okay, this AND operation becomes OR, and you take individual, okay, complement of individual variable. So x bar plus y bar plus z bar. Okay. Similarly, the other term which is written by x plus y plus z the whole bar. So here the OR operation and entire thing will take the complement. So by applying the complement, DeMorgan's theorem, we can write this OR operation becomes AND, and we need to take the complement of variable individual. So x bar into y bar into z bar. Okay, and we got this. And next we need to apply the DeMorgan's theorem for this particular question, which is x bar, y bar, z bar the whole bar. Okay, already the variable is complemented. So now we can try how we can x bar, y bar, z bar the whole complement. Now we can apply DeMorgan's theorem, and this AND operation becomes OR. Okay, so in this case we need to consider this. We are going to apply DeMorgan's theorem for this particular group. Okay, and when you apply DeMorgan's theorem, already there is a variable x bar. Okay, and when you split this again, there will be one more bar. Okay, and this AND operation becomes OR operation. So you'll write like this. Again, you need to take the y bar, then z bar the whole bar. And from the previous rule, we know the double negation. If you take complement 2 times, you will get exactly the same variable. So it becomes x plus y plus z. Okay, this rule we already explained in previous lecture. By Boolean rules, we know that double negation is equal to x itself. If you perform NOT operation 2 times, you will get exactly the same. And similarly, we can try the next question also. A bar plus B bar plus C bar plus D bar the whole bar. Again, we need to take the complement of the entire expression. So we need to take the apply the DeMorgan's theorem for this particular complement. And here you can see the already the variable is A bar, B bar, C bar, and D bar. Okay. And when you apply DeMorgan's theorem here, you will get this OR operation becomes AND here. So already there is A bar, and when you split this complement, it becomes A bar, again one more bar, and B bar bar, C bar bar, D bar bar. Okay, and again we can apply the double negation rule. So it becomes A into B into C into D. Okay, so this is the expression by after applying the DeMorgans. So this is the result. Now we'll do another question. Here apply DeMorgan's theorem to find the complement of the following expression. So here one expression is given f. Okay, this is a function actually. F is equal to a plus b plus c into d, and we need to find the complement. Complement means we need to find f bar, or we need to take the complement of a, b, c. This is the expression, and we need to take the whole complement. Okay, so in order to find that, we can apply DeMorgan's theorem. So there are two expressions. Now we can consider a plus b plus c as a one unit, and d is another unit. Let it be x, and so we can consider this term as x, and this particular term as y. So which is equal to, I can write x y the whole bar. So you can write x bar, okay, x into y. Actually, if you consider x is equal to a plus b plus c, that is x, and d is equal to y. So you can write x into y the whole bar. So if you split that, it becomes x bar plus y bar. So based on that, if you resubstitute, x becomes a plus b plus c the whole bar plus y is equal to d, so you can write d bar. Okay, now we can see that again you can apply DeMorgan's theorem here. If you split this a plus b plus c the whole bar, it becomes a bar, b bar, and c bar, and d is already there. So this is actually your f complement. Okay, so the expression you can see here. Okay, finally you will get this particular term. And now we can think about another thing. Again, a function is given, f is equal to abc plus def. Okay, two terms are there, abc one term, def another term. We need to find the complement. So f bar means there is a complement. We need to find abc and def, and we need to take the whole complement. So we can consider this term as x and this term as y. So if you write like this, it becomes x plus y the whole bar, and if you split, it becomes x bar into y bar by applying DeMorgan's theorem, and we can substitute here. So it becomes abc the whole bar into def whole bar. So once you practice, you can avoid this x and y. Otherwise, you try in this way. Okay, this group we can assign one variable, another group another variable. Then you will get a simple expression. And now we can resubstitute x is equal to abc and y is equal to df. And if you look at here again, you can apply DeMorgan's theorem here, because abc the whole bar. So you can write a bar plus b bar plus c bar. Okay, here this expression I can expand d bar plus e bar plus f bar. This is another term. So this is the final expression for this particular question, or f complement. Okay. Now we'll discuss one more question. Again, we need to find the DeMorgan's theorem to find the complement of this particular expression. So we need to find f complement. So to find f complement, here it is a bar b bar plus c bar d plus e bar f the whole bar. Okay. So now we can consider three terms here. Okay. X, y, z. So you can write x plus y plus z the whole bar. And if you split this, you'll get, or if you apply DeMorgan's theorem, it becomes x bar plus y bar plus z bar. And in place of x, you can substitute a b bar the whole bar, plus in place of y, you can substitute c bar d the whole bar. In place of z, you can substitute ef the whole bar. Okay. And again, you can split the here. It becomes a plus b, sorry, a bar plus b bar the whole bar. Okay. Not whole bar, again one more bar. Plus, again you can split this term cd, c bar is there, again you need to put a bar, and operation becomes or and b. Plus here e bar plus f bar. And you can simplify it, a bar plus b double negation means b plus c plus d bar plus e bar plus f bar. Okay. So I think I made a mistake. Sorry. Here we need to write. Okay. Actually, when you substitute x, y, z, okay, the whole bar, you need to write x into y into z. Okay. X bar y into z. Okay. Small mistake I made. Okay. Here we can see the correct expression. Okay. So finally, there will not be any plus. It's actually AND operation. So I made a mistake here. So please correct it. Okay. Okay. Thank you.